Hello guys, welcome to another episode of Cuda Education. This is a quick video. Today we want to talk about um, compute ray tracing. So compute ray tracing uses mathematical logic in order to simulate ray tracing. We are not using ray tracing hardware to simulate logic. We have a light source moving and shadows and all that stuff. We are not using ray tracing hardware. Now, in the case of in the case of graphics cards, in NVIDIA we had GTX and then RTX. We had G4 series and then the RTX series. The dividing line between those two cards was that the RTX series had ray tracing hardware, the GTX series did not. So the GTX series um, would not be able to run these ray tracing examples because it didn't have ray tracing hardware. That means acceleration structure, top level acceleration structure, bottom level acceleration structure, the whole ray tracing framework in computer graphics. Um, However, you would be able to still run compute ray tracing because it's computationally being done, right? We have our source file, which is CPU related, um, instructions, and then we have the shaders, which is GPU side instructions, right? Um, so compute shader based ray tracing. This sample implements a basic ray tracer with materials and reflections using a compute shader. Shader storage buffers are used to pass geometry information for spheres and planes to the compute shader. The compute shader then uses these as the scene geometry for ray tracing and outputs the result to a storage image. The graphics part of the sample then displays that image full screen, not to be confused with actual hardware accelerated ray tracing. Okay? So, not to be confused with actual hardware accelerated ray tracing. So, um, we're just doing computationally stuff. So older GPUs, as long as they are able to run Vulkan, you should be able to run this application. Now, what I want to do is when we run our application, notice that we are at 30 frames per second about, and you can see that it's struggling a little bit, right? What we're going to do is we're going to disable the shadow. We're going to disable the shadow and we're going to see what happens when we disable the shadow. So when we disable the shadow, notice that we still get the application. We get a bump in frames per second, uh, but we don't get any shadows, right? Animation runs a lot smoother. Still a little bit of stuttering, but it runs a lot smoother. But there is no shadow, so it's not as realistic. But we do get a bump of, we're at 45 frames per second, right? And that's all because of this shadow call right here, okay? So this shadow call is being called inside of, it's being called inside of render scene. So render scene is where we're rendering the scene, and we have this shadow call calc shadow is the name of the function, right? So calc shadow is up here, and here is calc shadow, right? So this is calc shadow that's being called inside of render scene, right? And this is the logic for calc shadow, okay? And it is what drives our example to give us the shadows. Notice that we have CPU side and we have GPU side. Shaders, anytime you see in computer graphics they talk about shaders, they're talking about GPU side processing. And a lot of the innovation and things that's happening in computer graphics is being done on the shader side. The shaders are sort of like icing on the cake. I mean, obviously, it's what gets the raw work done on the GPU, but it's really where a lot of innovation is happening. And notice that we have three different folders. We have GLSL, HLSL, and SLAN. Um, and the reason it's different shader languages because they're all competing to sort of bring new innovations to computer graphics and all of that stuff. The Vulkan API itself is sort of the foundation, right? And you want the foundation to be stable and predictable and don't have any bugs. Whereas the shader language is sort of like the icing on the cake, and you could be creative and you could try and do stuff, um, you know, even if they break, it's not necessarily the end of the world. But I know HLSL is Microsoft. Slang is like a relatively new language, but very innovative. And I think GLSL is, I believe it's the Kronos Group. I don't know, but um, you know, by default, these examples run the GLSL shaders. Notice that we also have three files for HSL, LSL, and Slang. We have two files, but we care about the GLSL stuff, right? So we have a compute shader, raytracing.com, a fragment shader, which deals with color and texture and stuff, and then a vertex shader, which deals with like textures and meshes and all of that stuff, right? Um, but this is where a lot of the innovation happens, and you know we are concerned with the we are concerned with the we are concerned with the shadow part of this application. So um, okay, right. So this calc shadow function. This function is a shadow ray test used in ray tracing to determine whether a point is in shadow relative to a light source, right? So, right, does anything block the light before it reaches the light source? Okay. If yes, the point is a shadow. If no, the point is lit, right? So we have the parameters for the function call. Let's look at, let me zoom in a little bit more. I can get rid of this now. Let's zoom in a little bit more. So we have calc shadow here, and we have where is it? Right. So we have our calc shadow position, light, vec, ID, t. So we have four parameters that we use in our calc shadow call right here, right? This guy right here. So four parameters that we use. So if we go up to one, two, three, four, okay. So what is ray zero? That's the first parameter. Ray zero, origin of the shadow ray, usually the surface point, right? Ray D is the direction towards the light, okay? Object ID is ID of the object that emitted the ray to avoid self-shadowing. Um, and T is distance to the light, maximum ray length. This gets updated if something is hit closer, right? So this is basically how far do you want the test to go? So do you want it to go all the way into outer space, or do you want it to just go, a couple of inches away um, a couple of inches away from the from where the ray was initiated, right? Because again, you're trying to figure out, does something block between you and the light source, but you have to declare the length of that ray that you're testing, right? What's the maximum amount of the ray? Like, let's say you don't hit anything after you hit the maximum length, so so for int I equals 0, loop over all seen objects, and we're basically looping over all seen objects. Before we even get to the looping over all seen objects, so we have ray 0, ray D, object ID, and float T. Let's look at how we actually so here is where we actually, so we have position. So POS is the origin of the shadow ray, usually the surface point. Um, Light vec is the direction towards the light. ID is the object ID that emitted the ray, right? So the ID of the object that emitted the ray, and then T is a distance that we're gonna maximum distance to the light, maximum ray length, right? So notice that T is defined here, length of UBO light position minus position, right? So basically we're going from the maximum distance between the point to the light source, right? So that changes, for each call. um, so let's get back to our calc shadow. So we're looping over all the objects in our scene, okay. You test a shadow ray against every object in the scene, right? So if scene object ID equals object ID, continue. So basically, you're going to skip the originating object. This prevents self-intersecting artifacts, what they call shadow acne, right? So we're not gonna we're gonna negate basically the originating object. We're gonna skip that. We're not gonna test for a shadow on on ourselves, kind of thing. Um, Initialize intersection distance. So T lock equals max length. Um, Distance to the current objective hit. T lock is distance to the current objective hit. Start at a very large value, meaning no hit yet. Let's move on from that. So object, this part is the object intersection tests, right? So we're testing now sphere intersect and plane intersect, right? So we're testing. We're basically we have the sphere intersect and plane intersect to see, does it hit an object, right? So we have a sphere and a plane. Um, does the shadow ray hit this object? If so, how far away, right? So basically, it returns a T lock, which is how far away. And then we do shadow test condition. So this is the core logic. So T lock is greater than epsilon and T lock is less than T. T equals T lock, return shadow. Okay. So here is where, we're testing if based on the intersection results, do we, are we going to return a shadow or are we not going to return a shadow? Um, Actually, just to hack this for a second, let us run. So right now we're running the application, right? And we see the shadow. Let us just not return shadow. Okay, so let us just hack this for a second. I do have to compile the shader. One second, guys. I have to compile the shader. And let us then run it without returning a shadow. So I didn't change anything except I'm not returning a shadow based on the logic, right? So I'm not returning a shadow, but like you could definitely see that like something in the place of a shadow is being returned, right? I'm hacking the function but you could see that like really we should be returning shadow, right? So that's that. But anyway, so let us continue. So we return shadow, update T to the closest hit, return shadow, likely 0, 0, similar. Okay. The point is in shadow. So what this basically means is that the point is in shadow, right? But T-lock has to pass all these tests before we get to here. So T-lock has to pass all these tests. It has to pass all these tests before we get to here. Okay. And then if we skip over this, then we just return one. Okay. Um, and that's our shadow test, guys. That's our shadow test. So, um, nothing too crazy here. Here is a zoomed out version of the file, view of the file. I mean of the function. So we have, we're basically just testing spheres and we're testing planes. Okay, and we call it inside of our render scene function. Um, and this is where we are in the bigger scheme of things. At some point, again, I said I will review the full script on the CPU side, the source code. But um, just wanted to go through that portion of the conversation. This is Cuda Education, guys. If you guys want to be able to run this stuff on your machine, you need to get tutorial number 1, which is installing the Vulkan SDK on a Windows-based machine with a Vulkan-capable GPU. So Windows based machine, Vulkan capable GPU. Um, doesn't have to be ray tracing capable, but it has to be Vulkan capable. And that's tutorial number one. And then tutorial number 13 is installing all of these examples, right? So you will install all of these examples. You have to install, you know, set up everything, the Visual Studio, all that good stuff in order to run this on your machine. Once you get that done, you'll be able to run, follow along, you'll be able to tinker with the code and get things done as you see fit. Anyway, this is Code Education, guys. I encourage you guys to get your hands involved in this stuff. We are already almost done with the first quarter of 2026. We still have 3 more quarters to go. Get yourself familiar with Vulkan so that in 2027 you could say, yeah, I know what Vulkan is and I know how to 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 look at stuff and get stuff done inside of Vulkan. So thank you guys for watching. Have a great day.